There are three types of blood vessels. There are arteries, capillaries, and veins. Arteries are going to take blood away from the heart, or capillaries are going to be between the arteries and the veins, and then the veins are going to take the blood back to the heart. Arteries are our highest pressure vessels, and so they're going to be designed to handle that pressure. And then they're going to get smaller and smaller. Our smallest arteries are called arterioles, and they're the ones that are going to feed into our capillaries. And capillaries are going to be the sites where we have gas and nutrient exchange with our tissues, and where we pick up the waste from our tissues to take and get rid of in our various organs. Like, for instance, our carbon dioxide waste, we're going to take that back to our lungs and get rid of it. Or if it's nitrogenous waste from our tissues, we'll take that waste to our kidneys and we'll get rid of it there. So this is our capillary beds, are our site of our gas and nutrient exchange. And there's much lower blood pressure in our capillaries because our capillaries are very fine and delicate, and we can't have high pressure there or it would obliterate our capillary beds. But our veins are the blood vessels where we take the blood back to the heart, but they're our sites of our least blood pressure. We have our least resistance in our veins because they have the largest lumens, the largest open areas on the inside. And we want the least resistance in our veins and the lowest amounts of pressure because blood flows according to pressure. And we have to have blood coming back to our heart, so we want the least amount of resistance in these vessels. The smallest veins are called venules, just like our smallest arteries are called arterioles. Our smallest our veins are called venules, and they're going to come straight out of those capillaries. We also call our veins capitance vessels because they can contain a lot of blood at any given time. Now, if we look at the structure of our arteries and our veins, and even our capillaries, we're going to have a certain wall structure. They're going to have an innermost layer, a middle layer, and an outermost layer, and those layers are called the tunica intima, the tunica media, and the tunica externa. On the tunica intima, or the innermost layer, it's going to be the layer that's in contact with the blood, or we could say it's in contact with the lumen, the open region, and that's the layer that's lined with endothelium, or simple squamous epithelial tissue. And underneath that simple squamous epithelial tissue, we're always going to be supported by areolar tissue, or in the book now, since we're out of chapter 4, we just call it loose connective tissue. The tunica media layer, or the middlemost layer, is made of smooth muscle and also elastin fibers for elasticity. And it's in this layer, because it's made of smooth muscle, this layer is going to cause our blood vessels to constrict or to dilate. And this layer is innervated by fibers from our sympathetic nervous system, and these fibers tell this layer to either constrict or to relax. And so this layer controls our blood flow. If this layer constricts, blood flow will be diverted to another region. If it dilates, blood flow will be diverted into this area. Or it controls blood pressure, because if it causes constriction, if this layer constricts, then blood pressure will increase in that blood vessel. If this layer dilates, then blood pressure will go down. Sorry if I babble a little bit. I've got a 9-year-old in front of me slurping in my office today, so it's a little distracting. Okay, the tunica externa is the outermost layer, and it's made mostly of collagen fibers, but there are also nerve fibers and lymphatic vessels running through it. And it also is interesting, in our largest blood vessels, it's got a layer of blood vessels running throughout the tunica externa called the vasa vasorum. So like our biggest blood vessels may be, say, the aorta, other vesicles like the superior vena cava and inferior vena cava, or I should have said those together, the vena cava together. They have their own outer blood vessels in the outer layer of the blood vessel itself, because the blood vessel is so thick, the blood vessel wall is so thick that it needs nourishment. So these are blood vessels in the blood vessel wall. So here's a picture of the wall structure. This innermost layer here is the tunica intima, and it's just simple squamous cells. So this is the endothelium, and here's the endothelium here, how it's drawn here, and we're comparing a vein and an artery, and here is a capillary. So in a capillary, actually, capillaries only consist of the tunica intima alone. No tunica media, no tunica externa. So here's just the endothelial cell itself, just making up the whole capillary. So usually it's made of just more than one endothelial cell, but this is showing you one endothelial cell wrapped, so the blood cells would be in here, shooting through here. So usually it's more than one. Might be just a little misleading here. But the capillary, it's a cross section through the capillary, and red blood cells would be in here. So tunica intima alone. Here's the tunica intima in an artery, tunica intima in a vein, very similar. But now if we look at the tunica media, totally missing in the capillary, but in the artery, look how thick the tunica media is. Very thick, because in arteries, we want to be able to control vasoconstriction and vasodilation. We want to control blood pressure in our arteries. Look how thin it is in our veins. In our veins, we don't want to constrict our veins a lot. In our veins, we're returning blood to our heart, and we don't want to restrict the flow of blood to our heart. So we don't want a thick tunica media because we're not going to be constricting our veins a whole lot. Get it? And so we don't have a thick tunica media in our veins. And look, by the way, look how large the lumen is in a vein compared to the lumen of an artery. Every time you see an artery and a vein together, you should be able to compare the two and tell which one is the vein and the artery, because the lumen of an artery is always much smaller than the lumen of a vein. Because veins, we want the lumen to be very wide open to allow blood to flow much easier back to the heart. It allows less pressure in this vessel. Now if we get to the tunica externa, in this picture it's called the tunica adventitia because that's what it used to be called. The tunica externa is very similar in the arteries and veins. So the big difference between these two would be the tunica media. We see the tunica media. And in the capillary, no tunica externa. So there's a big difference. Now the reason in a capillary we would only have the tunica intima is because in capillary these are the sites of nutrient and gas exchange and waste exchange, and so we want this to be really thin for diffusion and for filtration. So here's the picture that's in your book. In your book we had the small lumen in arteries and the large lumen in veins, and here's this inside we have the endothelial cells. We have the endothelial cells in here. Notice the thicker tunica media in the artery as compared to the vein, and we have this same tunica externa out here and the same tunica externa here. And the blood flow would be from this artery into the arteriole, into this capillary bed, out of the arteriole, out of the capillary bed, into the venule, and then into the vein. In that direction. If we take this capillary and we look at a capillary, really capillaries are just endothelial cells, and they'll have some supporting connective tissue around them. Always endothelial cells will have a scanty layer of irregular connective tissue around them. So this is showing you all the makeup of the tunica interna, media, and externa. Notice also that veins have venous valves. We'll talk about venous valves in just a little bit. Notice how our veins have a large lumen. And notice how small the tunica media is in the veins. In arteries, notice the smaller lumen. Notice the well-developed tunica media. Both of these things, a smaller lumen and a well-developed tunica media, will increase blood pressure. Both of those will increase blood pressure. Notice in capillaries that there's only a tunica intima. And the reason you would have a only a tunica intima is to enhance diffusion and filtration in the capillary beds. Now over here, having a large lumen in your veins and a small tunica media would allow blood flow to get better back to the heart. These are adaptations of veins to prevent, just to allow blood flow to get better back to the heart. Sorry, I'm being distracted by a 9-year-old. Okay, and also these venous valves are another adaptations of a vein to allow blood flow to get back to the heart better. What these valves do, this is not a good picture of a valve here because they've sliced into the valve. I'll go ahead and tell you that the valves in your vein are made just like the semilunar valves, like the aortic semilunar valve or the pulmonary semilunar valve. And if blood is flowing in this direction and it passes that valve, then it's going to fall back and get cupped into those valves so blood can't flow back down. So that's what venous valves are for, to prevent blood from flowing back down in your arms and in your legs against gravity. And so valves allow blood to flow only in one direction, and that would be back to your heart. So that's a great little setup that you have, your venous valves. So if we're just looking at the arterial system alone, there are, well, I can say 3 types of arteries, but really we're going to do 2 types of arteries. We have elastic arteries and muscular arteries. Your elastic or your conducting arteries, these are the ones that are going to be closest to your heart. And we call them elastic arteries or conducting a lot. They're conducting because they're conducting blood away from your heart. But they're also called elastic because they're very elastic. They have lots of elastin in them to allow them to expand when they accept blood from your heart. They are very low resistance arteries because they have very large lumens, and they have little to no vasoconstrictive properties. They're not going to constrict because we don't want them to constrict. We don't want them to put any back pressure on the heart whatsoever. So we don't have as many conducting and elastic arteries. Think of these as just basically the aorta and the largest arteries leaving away from the heart. Most of the arteries that we have are called muscular and distributing arteries. And when you learn the arteries in this chapter, most of the arteries that you learn in the body are classified as muscular or distributing arteries. We call them the muscular arteries because these are the ones that do the vasoconstriction to control blood pressure or dilation, and they distribute the blood throughout the body. Their lumen size is about 1 centimeter to 0.3 millimeters, about the size of a pencil lead. They do have the thickest tunica media because this is their job, is vasoconstriction to control blood pressure or vasodilation. And so that's what they do. They mediate blood pressure changes. And I'm going to show you a little picture next where we go from elastic to muscular distributing arteries. These guys, when they get smaller, then they become arterioles. And arterioles are any arteries that are smaller than 0.3 millimeters. And these guys are going to be the ones that feed into capillary beds. And when they feed into capillary beds, if they constrict, if the arteries constrict, then they're going to bypass the capillary beds whatsoever. They're going to bypass the tissues. If arterioles dilate, then the blood flows into the capillary bed. So that's how blood flow is going to go. Artery dilates, blood flows into a tissue, artery constricts, blood flow bypasses the tissue. Oh, my picture's not up yet. I guess we'll do it. Let me see. Here it is. So just to get you to this point right here, we had our elastic. Here's the heart. When it contracts, it's going to send blood into our elastic arteries, and those elastic are also called conducting. They prevent the blood from being pulsatile. The heart is it's pulsing, and we don't want the blood to be pulsing, and so they expand and they keep the blood flowing very smoothly through here. And then our muscular arteries are smaller and they're distributing that blood till we get down into our arterioles that are going to feed into our capillary beds. And the capillaries are what we're going to talk about right now. So we have a variety of capillary types. Make sure I didn't miss anything. These arterioles feed into our capillaries, and we have 3 types of capillaries. We have continuous capillaries, we have fenestrated capillaries, and sinusoidal capillaries. Our continuous capillaries are the ones that are going to be the least leakiest. In other words, the least permeable. Now, all of our capillaries are pretty leaky. but the continuous ones are the least leaky. They're found in your skeletal muscles, your skin, and in your brain. The ones in the brain are definitely the least leakiest continuous capillaries because of our blood-brain barrier. And we went over that a long time ago, a long, long time ago. There are more adaptations in these continuous capillaries that allow them to be the least leakiest of the continuous capillaries. But the skeletal muscle, skin, and the brain are where we find our continuous capillaries. And these are places where we don't want our capillaries, the blood filtrate, to leak out. And I'll show you in a picture why these are considered least leaky. Basically, we have tight junctions between them, and I'll show you in a picture coming up. Our fenestrated capillaries, they're like our continuous capillaries, except for they have things called fenestrations in them, little pores that have membranes in them. And they're found in our endocrine organs, small intestines, kidneys, and places where we want high absorption and filtration to occur. I'll show you with the fenestrations. Like in our endocrine organs, we are making hormones, and we're putting hormones into the blood. We're putting things out into the blood. In our small intestines, we're absorbing lots of nutrients. In our kidneys, we're filtering lots of substances. And so these are places where we need these fenestrations. In our sinusoidal capillaries, these are incredibly our leakiest capillaries. Absolutely, they have big, huge, gaping holes in these capillaries where massively large cells can creep through. So these are found in our lymph organs, like our spleen. They're found in our bone marrow. They're found in our liver. They're found wherever we're going to have high macrophage activity. In our liver, we have these cells called Kupffer cells, and these cells can reach through the sinusoidal capillaries and grab big substances to eat. In your bone marrow, those sinusoidal capillaries allow big cells like red blood cells to get right into the blood supply when they're made. So these are very leaky capillaries to allow large substances to get through. So here's our continuous capillary. These are our endothelial cells here. Here's one endothelial cell, here's another, and here's another. And so they do have tight junctions between the cells, but still substances can easily get through these endothelial cells. Very easily get through these regions called intercellular clefts. Skin, muscle, brain, that's where we'd find those. Now here's our fenestrated. It looks just like the last picture, except for in our cells themselves. Here's the cell. We find these little holes, but these really aren't holes. These are called fenestrations, and these fenestrations actually have little slits on them. Pretend like they had little membranes stretched across them, because they do. They're really not holes. They have little membranes stretched across them. So you just don't see it in this picture. Those are called fenestrations. So big substances can go right through these holes called fenestrations. So these would be found in our endocrine organs and our kidneys and in the small intestines, these type of capillaries. And our next one, take a look at the next one. We have big, huge, gaping holes. It looks like it's been moth-eaten. And then look at these big, huge holes between the endothelial cells themselves to allow substances, very large substances, to creep through those cells, and macrophages as well to get in and out. So this is a sinusoidal capillary. So we've done our arterial system, and we've done our types of capillaries. We haven't talked all about the capillaries yet. See these little things here? These are called precapillary sphincters. They divert blood flow in and out of this capillary. We're going to talk about let's see if we've got that next. Yes, we do. If we've got blood flowing through here, these are those precapillary sphincters here. If these sphincters are little smooth muscles that go around a tube. And if the sphincter is open, then it might as well not even be there. It's going to allow the blood to go into this capillary bed. So here's blood going through this arteriole. This arteriole is feeding into this capillary bed, and so the blood will go all through our capillary bed. This is actually the capillary bed here. If you look down here in this picture, everything in white here is the capillary bed. This little line here is called the met-arterial thoroughfare channel. Here's the met-arterial thoroughfare channel. So this region here is more like an arteriole. This region here is more like a venule. So we call it the met-arterial thoroughfare channel. And these little white things up here are capillaries, and these little white things down here are capillaries. If the sphincters are open, the blood will flow through the capillary bed and gas exchange will occur. And then the blood will flow out the other side and through the venule. If these little precapillary sphincters are closed, then blood will not flow through this capillary bed at all. It will be diverted right through the venule. An example of this: if you're not eating and you haven't eaten in a long time, blood will not be flowing through your small intestines. You don't need it. Blood will be flowing through the capillary beds in your small intestines like this. As soon as you eat, as soon as food enters into your small intestines, then the capillary beds open up and blood flows through like this. That's how it works. Blood is diverted to areas in your body where it's needed. Say right now the muscles in the back of your calves are not moving at all. Blood flow is like this. If you got up and you started standing on your toes, up and down, up and down, up and down, blood flow goes to your calves, and those little precapillary sphincters will open, and blood will be diverted to the back of your calves, just like so. If it had been in your gut, then it's going to go to your calves, and you'll stop digesting your food, and blood from your gut will be diverted to your calves, and then it will be diverted away from your gut. Blood is just diverted wherever it's needed in the body. So this term microcirculation, by the way, means blood flow through a capillary bed. Now on the venous side, venules are the smallest of the veins. They're only 8 to 100 micrometers in diameter, and they merge to form veins. So like we've said before, these veins are the lowest resistance vessels because they have a large lumen and they have a reduced tunica media. And they're called capacitance vessels because they're blood reservoirs. They hold up to about 65% of your blood at any given time. So most of your blood right now is sitting around in your veins, just sitting there. So because they have such a low resistance, we have to make sure that blood gets back up to the heart. And here are the adaptations that we have to make sure that blood gets back to your heart. We have venous valves to prevent backflow, and we have what's called our muscular and our respiratory pumps. Your respiratory pump creates a negative pressure. Every time you take a breath, every time you're breathing in your thorax, you create negative pressure, and that sucks blood back up to your heart. Your muscular pumps have to do with your muscles literally squeezing. Anytime you're wiggling your fingers, wiggling your toes, moving any of the muscles in your limbs, you're squeezing just a little bit at a time blood back up to your heart. It's called venous return. And also your veins have large lumens just to prevent resistance of blood flow. So when blood leaves the heart, it's going to leave through those elastic arteries, then go through the muscular arteries. It's going to go through the capillary beds where gas exchange is going to occur, and then it's going to be collected by the venules. We can call them post-capillary venules because they've just left the capillaries. And then those venules are going to merge to form veins, and it's going to go back to your heart. Now you see the lymphatic vessels that are here. We lose lots of fluid in our capillaries because in the capillaries, filtration occurs. And filtration is when we lose fluid, when fluid is forced through a vessel through pressure. And we're going to lose fluid in these capillaries. We always do. And that's called blood filtrate. Any of the excess fluid that's lost here and not resorbed through osmosis when water flows back in because of solutes, what we don't retain, what water doesn't go back through here through osmosis, any blood filtrate that's left out here is going to be picked up by your lymphatic system. And in these lymph nodes, we've got white blood cells that are it's going to cleanse that fluid, and it's going to cleanse it in the lymph nodes, and it's going to be returned into the venous system, and it's going to increase that blood volume. Any blood volume that's decreased in your capillary beds will be returned into the venous system near the superior vena cava. So one quick look at this graph and then we're done. This is showing you all the blood at any given time. Around 60% of your blood is found in your veins. Only about 15% is found in the systemic arteries and arterioles, 12% found in the pulmonary blood vessels, 8% found in the heart, and 5% found in your capillaries. So most of your blood at any given time is found in your veins. And that's it.